Okay, so today we will introduce a new chapter. We will start to talk about methods, numerical methods to find roots of an equation. So when we say the root of an equation, this means that if we have a function of x and we want to solve for x for which f of x equal to 0, this means that we are looking at the roots. Okay? And we have several numerical methods that are developed in this field because, in general, in any engineering application or in any physical problem, you might end up with an equation. And sometimes it cannot be solved by exact solution. So you need numerical techniques that will help you into finding what are the roots of your equation. In this chapter, we will consider bracketing methods. In next chapter, we will consider open methods. So just as the name indicates, when we say bracketing methods, this means that we will start from a certain interval, a certain bracket, including the root. And we will try to find it using techniques that will divide this interval until being very close to the root. Okay? In next chapter, we will introduce methods that will not need to know before an interval in which the root exists. So we can try start from any point and go to search for the root. We will see what are the advantages and disadvantages of each of these techniques. Now we will start with the bracketing methods. So first, in this chapter, we will find what are numerical methods that are common in engineering applications and can be used to find the root of an equation. We will introduce bracketing techniques, which represent a very important advantage over other techniques that they are guaranteed to converge. So I can be sure that if I give you a bracket including the root, you will be using this bracketing method, you will be able, okay, it will converge, it will be able to tell you where your root is. Now, we will learn to use what is the most appropriate method depending on the application. So we will see that each method will work better in some cases. So we will know in which case I should use this method, in which case I should use the other method. And we will introduce monotonic versus non-monotonic convergence, when we can say that this method is monotonic, when we can say it's not monotonic. Now, to start with, we will take a certain engineering application. We will start from the same example we introduced last time. So for the bungee jumper, so this is a very common example, and you will find in this book, whenever we want to introduce a new technique, they will give you an example on using this engineering application. So we have developed before that the velocity function of time can be written function of the mass, of the person, of the drag coefficient, of time. Okay? Let us say here, for example, if they tell us that we don't want to be on safe conditions for the jump, we don't want to exceed a velocity of 36 meters per second in the first 4 seconds of the free fall phase. And they gave us the drag coefficient, and the question will be what will be the maximum weight that can be allowed. In this case, all variables are known except the mass. So the only unknown, if we replace b by 36, we replace CD by 0.25, we replace T by 4. The only unknown in our equation is the mass. But this equation is not an explicit equation. I cannot find M by calculation, by exact calculation, just like this. Because as you can see here, it's a complex relation. So I will try to use numerical methods to find what is the value of M that will give me this equation. Since when we talk about roots, the form of the equation should be f function of m equals to 0. So all I have to do is to transform this equation into such type. I can easily do this by taking 36 to the other side. Or also I can take radical times hyperbolic tangent to the other side. So both will work, okay? The importance is that I get an equation that is equal to 0. So here, for example, if I take 36 to the other side, I will get 0 equals to radical times hyperbolic tangent minus 36. Or if I take this term to the other side, the equation will be plus 36 minus radical times hyperbolic tangent equals to 0. And it's equivalent because if you solve for f of m equal to 0, or you solve for minus of fm equals to 0, you will get the same roots. Okay, so both will give you the same result. Now, the simplest method one can think about is that to know nearly where my root is, I can, for example, take several values of m and try to draw my function. Okay, so if I take a number of points that is high enough, I can draw my function, and I can look at the intersection point with the axis of m here. Okay, I can draw f function of m or minus f of m because the root will be the same. Okay, so here this method can give you an approximate idea about where your root is, but it cannot give you very accurate results. So here, for example, you can say it's nearly around 140. But sometimes you know that in certain applications you cannot give a rough estimate. You should be accurate. So if you need very high accuracy, you need to develop numerical techniques that can predict the position of this root. Okay, and this is what we will do in this chapter. So to start with, okay, I want to know how can I know if I have a certain root, if it's how many roots I can have, if it's an odd number, it's an even number. To understand all of this, let us look at this graph. So first, if you consider, let's say, a certain function, and you know the value of your function at 2 points. So let's say you know the value at this red point is nearly 18, and at the green point it's also 18. So you can say that since both has positive values, so I might have or no roots in this interval. So in this example here, no roots. Okay, since all your terms are positive above the x-axis, so you don't have a root. If you have roots, the number of roots cannot be odd. It should be an even number. Because as you can see here, in case this curve will intersect the axis, it cannot intersect at only one point because you have the same sign for these two. So you need to have at least, if you have roots, it should be 2, maybe 4, maybe 6, but it should be an even number of roots. On the other hand, if you catch 2 points that has opposite sign, so for one f is negative, for the other f is positive, then you can be sure that at least I can have one root. I can have more, but in case I have more, it should be an odd number of roots, as you can see here. Okay, but in case the minimum possible number of roots will be 1. So no, there is no possibility to not have roots in case you catch 2 points with opposite f. Okay, with opposite sign of f. So this will help us into developing bracketing techniques. When we search for a bracketing technique, the initial bracket, the first condition to say that this bracket contains a root is that f at the lower end, okay, times f at the upper end should be negative because they should have opposite signs. So this is how we can say that this bracket will contain minimum a root in this way. Okay, now please stop me if anything is not clear. Let me check if you have any question. Karen, you were asking about which graph? If it's tangent to the graph, yes. This is a problem. I will talk about it. If it's just tangent to the graph, it's a problem. I cannot find it by the bracketing method. Okay, unless I am exactly at the point. So if I tried f at x and I got 0, so I can catch the root, but I cannot catch it in any other method. So because even if I take a smaller interval, still the 2 will be positive. So this is a disadvantage here. I can never catch this root using this method. Okay, so we will see example about this. So mainly now, when we say bracketing method, we need to start with 2 initial guesses that bracket the root. This is one inconvenience about this method because sometimes we need to iterate a lot to find what is the this interval. In general, I give you the interval. And for me, what is important for me is that you know to apply the technique, because sometimes searching for the bracket can take you a lot of time. Okay, so this is the hardest step, is to, in general, we do it in trial and error, or we draw the function so that we can see approximately in which intervals we have roots. This is also a possibility. Okay, but the advantage of these techniques is that once I have an interval with opposite signs of f, I am sure I can find the root. Okay, now in case in next chapter we will introduce open methods. For open methods, we can have just one single guess, or maybe also we can start from two initial guess depending on the method. But the main difference with the bracketing method is that they do not need to bracket the root. So this is positive, because even if I don't know where the root is, I can start by any point, and using the corresponding method, I can reach my root. While for the bracketing method, no. If I don't know, if I cannot say that f upper times f lower is negative, then I cannot find my root, because the condition to be able to reach the root is that it should the two initial guesses will bracket them. Okay, and this is possible when f upper when f lower times f upper is negative, because I can be sure that when they have opposite sign, and of course my function is continuous, this means that the root will be somewhere in between, and I will converge at the end, I can find. Okay. Now, this is an example on how you can do if I don't give you the interval, but as I told you, I will. Okay, but just to understand how we proceed if we don't have the interval, we can just, for example, say that if I want to find roots of fx between x0 and x6, I can start by dividing it into intervals. So let's say first I consider the first interval between x0 and x1, the second between x1, x2, the third between x2, x3, etc. I divide it into several intervals, and I try to find in each interval if I have roots or not. So for example, if I start with the first interval, you can see that f of x0 is positive and f of x1 is positive. So I can say, or I don't have roots, or I have an even number of roots. So to be able to know, I should divide this interval more. So I should, let's say I will divide it into two parts now. When I divide it into two parts, I will be able to say that f at this point is negative. So now I am sure that at least I have one root between these 2 points, and at least I have one root between these two. So I will be able to catch this this root and this root. Okay. Now between x1 and x2, whatever, if I take several intervals, I will never get a root, because no roots here, because always my function at the points will be positive. Okay, so whatever I do, even if I take a very small interval, I will not find any root here. This is why drawing the function can help us a lot, because if we know the behavior, it's going up and then down. Okay, and it's always positive. Since it's always positive here, it cannot have a root in this interval between x1 and x2. Now here we have a challenge here. You have several roots in a very small interval. So here you should take very small brackets to be able to trap your roots. So it will take a lot of computational time to be able to catch all of these roots. And between 4 and 5, this is, in general, the methods that we will develop will be used for one root in an interval. This will be the easiest case, because I can find in some number of steps, I can find the root. Okay. Now, the most challenging root is this one, which is just when the axis is tangent to the function, because I cannot trap it. So whatever, even if I take a very small interval, I will not be able to trap it unless I am just at the point. Okay. So this is how, in general, if you want to use bracketing technique, this will be it is called, the study is called incremental search. So I will continue to decrease the interval until being able, if possible, to find my root, except in the case where x is tangent to the function, that I need chance. If by chance I just try this point, it's fine. If not, I cannot find it using bracketing methods. So we will look at other methods and other chapters to catch it. Okay. Now, the first method, the first bracketing method is the bisection method. Okay. And what is the concept of this method? It's very simple. The concept is I start from a certain bracket. The condition, as we said, to say that this bracket will contain minimum a root is that if I calculate f here at the upper point, at the lower point, and f at the upper point, they should have opposite signs. This is the case here because f lower is negative while f upper is positive. So I am sure that I have a certain root in between. And as you can see here, this yellow point, full point here, is the exact solution. And I will try to approach this solution. So as a first estimate of the solution, in bisection method, as the name indicates, I will divide the interval into two. So first, the first estimate of my root, this is estimate 1. I just take the middle of my interval, okay? And I say this is, for me, this is the first estimation of the root. This is XR1. Now, what is the next step? I look at what is the function at XR1, and I look at its sign. If FXR1 is negative, then I can be sure that the root is now between FXR1 and F upper, okay? So X is between XR1 and X upper. And in this case, the new interval will be this one. So now I will take, this is my lower point, and the upper point will remain the same. Okay? Now, in the next step, I say I will divide this new interval. So this is my new interval. I will divide it into two parts. So I will take a new estimate for my root. So this is XR at 2. And also, I will check the sign of FXR2. FXR2 here is now positive. So what can I say now? So my root then, okay, so this is FXR2 is positive, while FXR1 is negative. So now I can be sure that my root is between XR1 and XR2. And you will see now that if I continue if I do now an iteration, I will be very close to the solution. Because if I just take the middle of the interval between XR1 and XR2, I will be very close to the exact solution. So by doing a certain number of iterations, I can be very close to the solution. And of course, to know where to stop, I should have a criterion. The criterion can be, they can tell me you can maximum do 5 iterations, for example. So I will stop at 5 iterations. They can tell me you should stop when the approximate error is less than 1%. So I will continue to do iterations until reaching this point. And in such problems, okay, in general, which error is involved? The true error or the approximate error? They will ask us to find the relative true error or the relative approximate error, do you think? Yes. Why, Leia, it's the approximate?
Because we're not sure of the exact values.
Exactly. So in general, why to do these methods if we know the exact value? It's meaningless. If I know the root, why I want to search for it? So in general, when we do this procedure, we don't know where the exact root is. This is why we will not be able to find the true relative error. Sometimes they told us, no, the root is given just for us to be able to calculate what is the true error. Okay, but if we have a certain application, if we want to find in general the root, we don't know it previously, so we will find the relative approximate error in this case. Okay, so we will just compare from iteration to iteration what is the error involved. Okay, so now in summary, this will summarize the bisection method procedure. Okay, the first step is to determine a certain bracket containing the root. As we said, this step I will do it for you. I will give it the bracket, okay? And how you can make sure that this is the bracket I gave you will contain the root? All you have to do is to verify that f lower times f upper is negative. Then you can be sure that I have a root in this interval. Now you start with an estimate of the root. Okay, so you estimate the root as xl plus x lower plus x upper over 2, just at the middle. So this is in case of bisection method, you take it just at the middle. And now, once you find x root, you must compare with the previous iteration. Okay, so you will calculate the approximate error to see if your criterion is satisfied or not. So you do xr new minus xr old over xr new, and you compare with a certain criterion. This will be given to you. It can be 1%, 2%. It depends on the accuracy required in your problem. So in this case, this can be a criterion, or also another criterion can be if they tell you you can do maximum 10 iterations. So you will stop at the 10th iteration and say this is my estimate of the root. Now, after this, if your condition is not satisfied, if your criterion of convergence is not satisfied, you should continue to iterate. You should get a new bracket, okay? How to know what is the new bracket? As we said, you compute the function value at the root you found, and you say, I will check, is f of the root times f of the lower end of my bracket is negative, then I can be sure that my root is between xr and x lower, okay? So if I will just give you here, if I put it here, this is x upper, this is x lower, sorry, this is x upper, okay? And you found x root in between. You evaluate the value of f. If f at the root times f of the lower end is negative, this means that the root is between these two. So my new interval now will be between x lower and x of the root. This means that xr will replace now x upper, while x lower will remain the same. So in this case, when fr times fl is smaller than 0, I set x upper equal to xr, while I keep xl as it is. Okay? On the other hand, the other possibility, if fr times fl is positive, this means that I already have, this is x lower, this is xr, and this is x upper. When f at r is opposite in sign is to f at upper, so it's of the same sign of x lower, then the root will be somewhere between xr and x upper. So my new interval in this case will be xr, which I calculated, with x upper. So now I should replace in my new bracket, x lower will become xr, while x upper will remain the same. Okay? And I will repeat this procedure until the criteria is satisfied. Just here, you have a typing error. It should be opposite. I will fix it for you on the slides. Okay, on the slides posted on Blackboard. So in bisection method, you have epsilon true is always smaller than epsilon approximate. And this is a very important property. I will demonstrate this for you. This is a very important property of the bisection method, because once the criterion is satisfied for epsilon approximate, I can be sure that also epsilon true is smaller than this value, so I am on the safe side. Okay, just let me check the questions. I will give you just the first interval. Okay, Mark? Once I give you the initial bracket, you should conclude what is the new interval for the second iteration. Of course, I will not give it for you. I just give you the initial one. And as we demonstrated, this is the technique that you will proceed with in order to find what will be your new brackets. Okay?
Doctor, can you repeat please step 4?
Yes, of course, I will. Okay. So the idea is, okay, you have, I will give you an example. You have, let's say we are considering the interval between you have a root between 1 and 3, and you want to look for it, okay? When you calculated f of 1, you get a negative value. Let's say it's -1, while f at 0.3 is +2. So you can be sure that your root is somewhere in between, okay? So using the bisection method, what you will do, you will say, I will consider as a first estimate that my root is xr1 is equal to 2, okay? Now, how to determine what is your next bracket? You evaluate f at 2. So you say, I calculate f at 2. For example, if I get it equal to plus 0.5, for example. What can you say now? Now, f of 1 is -1, while f of 2 is positive. So now you can say that the solution, your root, will be between 1 and 2, because f1 is opposite in sign to f2, while f2 and f3 have same sign, okay? So it's impossible to have your root between 2 and 3 because they have same sign for f. So the root, of course, will be between 2 and 1, somewhere here, okay? So then you say, because I have opposite sign for f1 and f2, then the root is between these two. And now my new estimate for xr will be 1.5, okay? Now, for example, if you got f at 1.5 and you got it's a negative result, so f at 1.5 equals to -0.3, for example. Now you can say, because f at 1.5 is negative, while f at 2 is positive, now I can say the root is between 1.5 and 2. Okay? And you repeat until reaching the desired criterion. Yes, هلا غادي we will do another example by step, but is it clear now? What is... Yes?
يعني أنا ما ضروري استعمل الثيرد، دغري فيه نط على الفورث ساعتها.
What do you mean by force?
يعني الفورث ستيب، يعني الثيرد ستيب ما لها عازة.
بلا أكيد لها عازة. الثيرد ستيب كيف بدك تعرف وين بدك توقف؟ يعني أنت تنقول قلت لي إنه السوليوشن بين 1 و 2. اتفقنا؟ كيف تعرف إذا لازم كمل أو لا؟ ساعتها بتقول I will check if the approximate error, يعني if you compute f at 1.5, okay, and you compare it with f at 2. إذا أنت الapproximate error أصغر من stopping criterion ما بتكمل، ما بتاخد interval جديد. You stop.
اوكي ساعتها باخد الاكس ار مع شو؟
ساعتها ما هي شو الايديا؟ الايديا انه انت اخر شيء ما رح تقدر تلقط اكس ار 100%، بس بتقدر تقول انه هي بهالانترفل، يعني تنقول انت اخر انترفل اخذته اوكي كان 1 2، ساعتها بتقول as a rough estimate حتكون root 1.5 and this will induce only an approximate error of less than 1%, let's say. So I can stop. I can approximate the root by 1.5 with a good accuracy.
يعني أنا الثيرد ستيب هي بس ما أتعذب أعمل الفورث، يعني أنا كان في وقف على التو.
مظبوط.
أوكي.
أنت بدك تعرف وين توقف وإلا ما بتوقف. If you don't have a criterion, you can never stop. رح يضل فيك تصغر الانترفال أكثر وأكثر وأكثر. You can do infinite iterations. But this is why you should have a criterion to stop. At which stage you stop, it will depend what is the accuracy you want for your solution. Okay?
دكتور يعني بس أعرف وين in general، يعني بس يصير أعرف in general وين الروت. دغري بجيب الأرر كرمال نشوف صار أصغر.
مزبوط. على كل ستيب، يعني كل ما أعمل بس أول ستيب ما فيني أعمل ايرور، يعني أنا بس جيب XR1 لأنه هيدي الفيرست iteration. أوكي؟ إجباري الفيرست iteration ما فيني أعملها comparison لأنه ما في شيء قبلها، إجباري أعمل at least another iteration. أوكي؟ and I from here I do the approximate error. إذا من الأول من دغري كانت smaller than the criterion I stop direct. If not, I will compute now XR3. Okay? And then do the approximate error between 3 and 2. I will repeat this procedure until satisfying the criterion of convergence. بس أوصل له I stop. Okay, yalla, we will do a numerical example so you can understand it any better. Okay? Let us take an example. If you consider the same example we talked about before, we want to find the value of m in a way انه this function of m equals to 0. مثل ما قلنا أخذنا 36 to the other side أو فينا ناخد the function to the other side. So we get that 36 minus this function should be equal to 0. Okay? Now, we have considered the graph and we said that approximately the solution is about 420. Let us see how the bisection method can give us an accurate result. أنا حاطيكم البراكت. So the initial guesses are given for you. I will consider that my mass will be between 50 and 200. To verify that this is true, all I have to do, I replace m by 50 in the equation. I will get a positive result. Okay, so this is f lower at stage 0. يعني initial bracket lower part هي 50 والupper band هي 200. Okay, so if I evaluate my function at m equal 50, I get a positive result. If I evaluate my function at m equal 200, I get a negative result. So it's fine. I am sure that I have a root in this interval. Now, second step, I do a first estimate of the root. I take 50 plus 200 over 2. So a first estimate for my root is 125. Okay. Now, as a first step, I cannot compare it with something else. I cannot do any error calculation. I need, of course, a second step. Okay. So now to do the second step, I should find f at m equal to 125. So if I replace m by 125 in this equation, I want to know if it's a positive result or negative result. Okay, I get that f at 125 is positive. So if I compare, I have f lower is a positive, and also f of the root is positive. So of course the root is not between the lower band and the root. It's between the root and the upper band. So I can be sure now that my mass will be between 125 and 200. So my new interval, instead of the lower band, will be replaced by 125. So I will put 125 instead of 50. And the upper band will remain as it is. Which is 200. Okay. Now I can compute a new estimate for my root, which is 125 plus 200 over 2. So my new estimate for the root is 162.5. Now I have two estimates, so I can check for the approximate error. The approximate error is 162.5, which is the new value this is what we call the m new, because it's a new estimate, minus the old estimate at iteration 1 over the new estimate. So if I do the comparison, I get 0.23, which is nearly 23%. So I should compare to a stopping criteria. Let's say the stopping criteria is 0.2, for example, 20%. So I am not, until now, I didn't satisfy the criteria. I should continue. Okay. Now, the next step, same procedure. I should evaluate what is the sign of f when m is equal to 162.5. Okay. When I do so, I have the f lower, okay, is f at 125, which is positive, and f of the root is f of 162.5. If I calculate it, I get a negative result. Because the product between f at the lower band and fr is negative, this means that the root is between the lower part and xr. So now I can be sure that my mass is between 125 and 162.5, somewhere in between. So my new bracket is 125, 162.5. Now I can do a third estimate for my mass, which is m lower at stage 2 plus m upper at stage 2 over 2, which is 143.75. If you remember from the graph we got, it's nearly 140. So we can say that we are close to the solution. You can make sure now by calculating the approximate error. The approximate error is 13%. which is lower than 20%, which is the criterion of conversion. So I can stop here. Of course, it's still not maybe a very accurate result. An error of 13% might be high in some applications. So you can set a smaller criterion, convergence criterions, but in this way you will need to do more iterations. Okay? Is the method clear? Yes.
Can you repeat step 4, the slide before?
Yes, of course. Is this one?
Yes, please.
Okay. Look, in step 4, you should update your interval. Okay? And you started from an interval of 50 to 100. Okay? In each step, you will reduce the length of your interval. Okay? It will be reduced by 2 because you are taking a point at the middle. But now you should decide what is the new bracket. If I should take the middle point with the upper bound, or I should take the middle point with the lower bound or with the upper bound. Okay? How to decide what is your new bracket, this one or this one? You should check for the condition. In order to have the root in any of the two brackets, the condition is that when I define my new bracket, the function at one end times, so this is the lower end, times the function value at the upper end should be negative. Yani the sign should be negative to make sure, because they have opposite signs, that the root is in between. Okay? So now you say, I have the middle of 50 and 200 is 125. But now, what is my new interval? Is my new interval 50, 125, or 125, 200? To know this, you should find f at each point. You already calculated, this is f at the lower end, which is f at 50. Okay, f at 50 is positive, while f at 200 is negative. Okay, now to check what is the new interval I should take, I should now calculate what is f at 125. F at 125 is positive, it's equal to 0.41. Because f at 125 is positive, okay, this means that f50 and f125 have the same sign. So the root cannot be in this interval, okay? Because when you define a bracket, to have the root in the interval, should have opposite signs of f at the two ends. So you can say now, because f at 125 is positive, while have f at 200